Hi, I'm going to explain really quickly distance, time, and then velocity time graphs. So here we've got a distance time graph. You can tell the difference between the two because this one's got distance written on the side here. I've just chucked some numbers on to help us with talking about this. So we've got time along this bottom axis, I've got distance up the side here. So if we were to describe the motion of this object, we'd say that it's moved away from its origin, and then it's gone a bit further, and then it's come back towards where it started, and then it stayed stationary, or it stayed still in this end section here. Now the important thing about a distance time graph is the gradient of the line. So if we consider how steep the line is here, if you notice it's much steeper than this section here. So if we were to do some maths, this one has gone between 2 and 5 in 2 seconds. So that would be 2 divided by 2, which would be 1 meter per second. Now this one here has gone from 0 to 5 in 2 seconds. So 2 on the bottom, 5 along there. So that's going to be 5 divided by 2, which is going to be 2.5 meters per second. So you can see here where the line is steepest, this is where we have the highest speed. Okay. Now if we do the same on this side here, it's gone from, it doesn't matter what side you draw the triangle on, it's taken 2 seconds across the bottom, and it's gone down by 4. So here we've got a negative. You see how it's come backwards here, so it must be moving backwards at 4 divided by 2, which is 2 meters per second. Okay. Now along the bottom here, just to check that that actually works, we've got no change divided by 2 seconds. So 0 divided by 2 is 0 meters per second. And that is everything you need to know about a distance time graph. Now, my next one is a velocity time graph. Again, you can see we've got velocity, we've got time, just about squeeze it onto the sheet. So time down here, so we've got seconds and meters per second on the side here. Now, this time, the slope of this graph is equal to the acceleration. So if we do the triangle here, then what we're going to get is we've got 2 along the bottom and we've got 10 going up there. So 2 and 10. 10 divided by 2 is equal to 5 meters per second squared, which is the unit for acceleration. Along the top along here, we've got no change in velocity divided by some time. I think that's supposed to be a number 5 down there. So we've got no change here. So this object is not accelerating. It's at constant velocity, which is something that confuses people sometimes. People might say it's stationary, but that is not true. It's still moving forwards at this point here. And then we've got on its way back down, I'm just going to do my thing again here. So it's gone down by 10, and that's at 1 second. So I've got 10 meters per second squared this time. Okay, so the gradient of these lines is equal to the velocity, the acceleration of this object. But there is an extra thing that we can do, particularly if we're in the higher tier. Because velocity is effectively speed and time can be used to find distance traveled, okay, because the distance traveled is equal to the velocity times this time, that is the area underneath this graph. So if we simplify it a bit so that we've got 3 sections, we can do a little bit of cheeky maths and find out the area underneath and therefore the distance traveled. So 2 times 10 is 20, but because it's a triangle, we're only going to do half of that, which is going to be 10 meters. This bit here has got, we're 3 along the bottom and we're 10 up. So that's going to be 3 times 10, which is 30. And then lastly at the end here, I've got 10 again times 1 second halved, and that's going to give me 5. So I need to take all of those together, and that's going to give me 45 meters. Okay, so really briefly, the acceleration is the gradient of this velocity time graph, and the area underneath the line is equal to the distance traveled. All right, that's all for now.